So, in the earlier modules we discussed the RBF. I mean I am going from reverse chronological order. We discussed the RBFs, before then was the MLP and before then was the perceptron. So, we studied various algorithms. So, we revisit the same problem here. How can we do pattern separability? I mean assuming it is a linear, if you have linearly separable patterns, how can we decide on the optimal hyperplane, and if the patterns are non-linearly separable, is it possible to revisit this problem again in the context of a hyperplane that can be done in possibly a different dimension than what we have with our initial dimension, in such a way that we can get linear separability possibly in higher dimensions. These are some motivating questions that we have to ask. But before we delve into the details, just a sort of an idea where we started off with. We were with the perceptron and we said the perceptron can give us guaranteed convergence, and we can find a hyperplane to separate two classes that are linearly separable, right. We have points in two classes that are linearly separable, and we can have a plane that can separate them. But the problem with the perceptron was that there was no unique solution. You can have infinite different hyperplanes that can separate the two classes, provided they are linearly separable. Then we extended this notion of perceptron to the multilayer perceptron, where we got in this activation function, and we said that we can get decision boundaries that are essentially non-linear. So, classes that are non-linearly separable can be separated using discriminant boundaries that are essentially non-linear, because we dealt with MLPs that had non-linear activation functions, right, and we discussed the architectures and all the details. Then we moved on to the radial basis functions, again a class of non-linear activation functions, non-linear functions in the hidden layer, but linearly combined using certain weights between the hidden layer and the output layer. So, this also solved us this problem of non-linear separability. But here is a question, I do not want non-linear separability for, I do not want to have discriminant boundaries that are non-linear, because it is difficult for me to deal with those. If instead I want hyperplanes that can separate the classes, but I know in my initial dimension I cannot do this, because it is given the data points in say an m dimensional space, they are not linearly separable. Can I do something by going to higher dimensions that I can formulate a hyperplane that can separate these classes? So, the motivation to that led us to Cover's theorem, etc., but we did not see through the details in terms of practice as to how one can go about doing this. So, in this module we will discuss support vector machines as a powerful tool in solving some of the problems that I discussed earlier, right. I mean it fixes some of the issues with the perceptron that we had in terms of arriving at a unique solution, then have multiple solutions that are not unique, and then the roots to this are with a hyperplane, right. It is still dealing with this linear geometry in some sense. Okay. So, let us begin with our journey with this. So, SVMs they are another class of algorithms for pattern classification and nonlinear regression. And this is a linear machine because we are still interested in the form of a hyperplane W transpose X plus B in this form, right. In this form we are interested, it is still a linear machine, and the roots to these support vector machines are from the work of Vladimir Vapnik and this is a very elegant theory with firm roots in convex optimization. Okay. Now, what is the basic idea behind SVMs? The idea is as follows. We would like to construct a hyperplane as the decision surface. Unlike MLPs and the RBFs which could have nonlinear decision boundaries, here in this case we want hyperplane as the decision surface in such a way that the margin of separation between the two classes is maximized. But this is very important. We want the margin of separation between the two classes to be maximized. So, I have one class here, another class here. So, there is this boundary here that I want to set, right. I want to, this distance of separation should be in some sense optimized, right. This is class 1. And this is class 2 and this is the hyperplane. Okay. And the idea of deriving this hyperplane stems from the notion of structural risk minimization. That is, we formulate an objective for each of these classes C1 and C2. It gives us two different labels, say +1 and -1, and we want to derive a hyperplane that minimizes some functional, and that functional happens to be a risk function that depends upon the data points and the labels associated with the data points, etc. right, and this is how we want to work with this problem. Okay. In the case of linearly separable patterns, we need to derive a hyperplane that solves our objective, right. We can have multiple planes which can separate the two class of points. So, we want to arrive at that hyperplane which in some sense is unique, subject to certain constraints such as that we want to increase the margin of separation, right, that is one constraint that we want to kind of impose. And in the case of non-linearly separable patterns, we lift the data points, or I would say we need to lift the data points to a higher dimension so that we can still derive a hyperplane that solves our objective, right. There are two cases, linearly separable patterns and non-linearly separable patterns. For linearly separable patterns, we need to derive that optimal hyperplane. For non-linearly separable patterns, we need to lift the points. So, for example, I have in a two dimensional space points like this, clearly there is no hyperplane, this is say in R2. From here I need to possibly go to R3, and in some geometry in R3 I have a plane that can separate these points. So, some transformation T going from R2 to R3 that I can have a plane in R3 that can separate these points. So, this is sort of the idea. Now, let us go slightly deeper into this topic. A notion central to the SVM is the computation of the inner product between a support vector xi and a vector drawn from the input space. And these support vectors, I will discuss what the support vectors are, but you can bear with me till that moment. So, these support vectors are a subset, or I would say a small subset of vectors of the training set. They are a small subset of vectors of the training set extracted by the algorithm. So, here I would possibly, instead of inner product, I would say inner product kernel would be the right idea here, because I have an inner product kernel between a support vector and a vector x drawn from the input space. So, I will discuss what the support vectors are and the geometry of the support vectors over the next set of slides. So, let us discuss the geometry of this problem, right. We want an optimal hyperplane for linearly separable patterns, right. We want an optimal hyperplane towards linearly separable patterns. This is our objective. And what are we given? So, we are given data which comprises of our training samples. So, I would say consider the training samples xi and d suffix I equals 1 to capital N, where x suffix I is input pattern for the ith example and d suffix I is the target or the desired response, is what you might call. So, we assume that the patterns represented by d sub I, which is basically belonging to +1 or -1, is linearly separable. Okay. This is an important assumption that we have, because we are dealing with optimal hyperplanes for linearly separable patterns. The equation of the decision surface is given by W transpose x plus bias equal to 0. Okay. Now, W transpose xi plus bias is greater than or equal to 0 for d suffix I equals +1 and otherwise, that is W transpose xi plus b is less than 0 for d suffix I equals -1. So, if you imagine this x1 x2 plane, let us just imagine this in 2 dimensions. So, we have all these points indicated by these crosses, and we have some set of points that are indicated by these circles. This in some sense is my optimal hyperplane with a certain margin rho naught, and those set of points that are critically lying on these boundaries, they are my support vectors. So, they are data points inside the training set that is extracted by the algorithm, and that is how it works, and they are critically lying on these boundaries. See, I can have many hyperplanes. The perceptron can give me many hyperplanes between these two classes. So, let us say this is class 1 and this is class 2. So, I can have different hyperplanes that can form decision boundaries between these two classes, but there is one optimal hyperplane that I want to maximize the margin of separation, and that is my objective towards this goal. Let W naught and B naught be the optimum values of the weight vector and the bias. So, we have W naught transpose x plus B naught equal to 0 is the equation of the decision boundary, right. Decision boundary is given by this equation. Let us write the discriminant function. So, for every point x, I can evaluate a function called a discriminant function, and depending upon what it evaluates to, I can figure out if it is +1 or -1. So, let us write the discriminant function as g of x, which is equal to W naught transpose x plus B naught. Now, from our notion of the normal to a plane, right, from our basic coordinate geometry, any vector x can be written as xp plus r times this vector W naught upon norm W naught, right, sort of simple geometry that you can visualize here. So, this is this vector W naught, which is normal to this plane, and if I think of any point P with a position vector x, then you can express this in the component which is perpendicular to this plane and which is along this plane, and that's how I have written this down. And r is this algebraic r is the algebraic distance between the point and this hyperplane, right. So, just put in 2 dimensions. I give this point x, this is the algebraic distance of the point x with respect to the plane, and so therefore it is in the direction of w naught. So therefore we have to express any vector x as xp plus r times w naught upon norm w naught, right, and xp is this, right, and this is the direction of w naught, and you normalize it you get the normed the direction to be normalized to unity. So this is the direction, this is a unit vector in this direction, right, this is the direction, and r is at distance that you will have to scale. So I write it again. So xp is projection of x onto the hyperplane, and I am indicating this as my hyperplane. So I think we are complete in this form. Okay. Now bear in mind r is positive if x is on the positive side of the hyperplane and it could be negative if this is on the negative side of the hyperplane. Okay. So if it is on the positive side of the hyperplane on this side, it is positive. If it is lying on the negative side of the hyperplane, then r is negative. So we will end this lecture here.